So it's a great pleasure for me to introduce today Professor Gioele Zardini from MIT. His work on compositionality has taken a great kind of ride, and he is having huge impact on autonomous systems. He's a recipient of many awards, including DARPA Young Investigator Award that he just got this week. Congratulations. And with that, let's get going. You get started and we'll take it from here, okay? Thanks, Gioele.
Thanks so much, Naira, for the invite, first of all, and second, for the kind introduction. So yeah, I want to talk today a bit about my vision for these compositional tools for system design. You will notice that I will touch on many points, and mostly I will open problems rather than close them. But really, my goal is to get more people excited about this topic, is to show you what we are doing, and possibly to have overlaps or collaborations going forward. And yes, so mainly I will be talking about society critical systems. But what I wanted to start with is a slide saying, you know, everything I present, it's not only work done by me. One of the perks of becoming a PI is that you get to create a group and actually have very bright students coming and working with you. In my case, it's mostly people that like to eat. So I couldn't find pictures where we weren't going for a dinner or something similar, but I will mention the specific names of the specific students I have whenever it's due. All right, so I want to start with kind of an overview of some of the things that are ongoing in the group that I think will provide sort of a motivation for some of the questions we are asking. So in general, we work on a variety of systems, you know, ranging from intermodal mobility systems, where you have various modes interacting, sometimes even interacting with energy systems. We work a lot on multi-agent autonomy, where you have to design the vehicles together with the coordination schemes. We have a bunch of work in more classic design disciplines, for instance, challenges such as designing ships or retrofitting ships given some constraints. We just created a maritime shipping consortium here at MIT, all the way to things like designing soft robotics, all the way from algorithms to actual materials, and even some stuff in automotive where you have to design race cars together with the strategies. Now, this might look like a weird mix of things where the common denominator is not clear, but there is one. And it is that essentially the societal impact of all of these technologies really depends not only on the technology itself, that sometimes is developed in isolation, but really on the joint design and the joint orchestration with existing systems and existing infrastructure, right? A good example is mobility. One thing is designing an autonomous vehicle by looking at the case of an autonomous vehicle in isolation, in a lab, and so on. The other one is how does it impact actually an existing system, an urban ecosystem, for instance. And in this context, there's always the two sides of the spectrum, right? It could go very well, and you could solve a lot of problems. For instance, autonomy could reduce the number of cars on the road. You could make public transit even more convenient and attractive and use this solution just for first and last mile transportation. And there are studies showing that overall things could become more affordable or sustainable. On the other end, it's also clear that when designing or operating these technologies suboptimally, you could increase congestion, or worse, you could even make solutions that are less sustainable than you started with. Now, I don't argue for one or the other. What I'm saying is that we slowly understand well single components, but we still lack tools. Oops, do you still see me? Yes, but we still lack tools to understand the co-design of interconnected systems, right? Slowly, the single components are mature, but we still don't know how to design interconnected systems. So today's talk really goes into more detail of this. We ask the question of what is compositional design for engineering systems, and I will show you some tools that we are developing to solve these challenges. And then I will close the talk by really talking about what are the open challenges, what are the open problems, and what is that we are trying to do with that. Now, everything I talk about can be found on our website. There you will have pointers to papers and so on. And I'm really happy also to take some questions offline if today's time does not allow to discuss more in depth certain specifications. And feel free to ask questions any point. I don't see you, as I told Naira, but I hear you. So as soon as you have questions, please let me know. All right, let's get started. Really, my vision for automated co-design is kind of a broad one. I don't necessarily think about robotics as the only example, right? I think about design as the activity of trying to minimize some resource usage. This could be externalities of that technology, CO2 emissions or congestion in a city, but it could also just be dollars spent or time needed to perform some task. And now this is subject to some functionality, some task, some specification you have for your system. It could be serving the demand in a city. It could be following a trajectory for your aircraft, whatever you want. And now some of the technologies we are developing essentially allow you to create a language in which you can clearly specify tasks. You can clearly specify some knowledge from multiple domains, and you can clearly specify some design options you want to choose from. Parameters in an algorithm. It could be sensors to put on a vehicle, or even the design of a network for a particular service. And now you want some magic to happen, and now you want some optimal designs to come out, or some recommendations to come out of this system. Now let's be a bit concrete, because I know this could look like end wavy stuff. If you're thinking about autonomous vehicles, you want a language through which you can specify tasks, say distributions of scenarios you could encounter, principles, so for instance, robot autonomy and physics principles, and now the actual things you are designing are components or algorithms, right? For instance, perception, control, planning, or even end-to-end architectures. And now, when you will evaluate various solutions, you will evaluate them based on trade-offs. For instance, errors with respect to the tasks and energy consumption. Now, you might not care about autonomy, but in mobility design, this is a quite similar task, right? You want to focus on some specification. In this case, is maybe demand. People that want to move from origins to destinations with certain preferences from what they like. And now the principles are from network theory, operations research, infrastructure design, and the things you are designing are the services themselves. The fleets, the kind of vehicles you want to use, the networks on which they should operate, and even the policies, pricing or these kind of things. And again, whatever you design some solutions, you will evaluate them based on trade-offs, many dimensions. Here, for instance, performance and investments. Now, why is it hard to come up with the magic inside this box, which is essentially what we're trying to do? There are at least 3 reasons, right? The first reason is that making decisions about these systems requires knowledge and specifications from different domains, right? Even if I choose a very specific task, such as the one of designing a fleet of autonomous vehicles, which is kind of a niche one, you have to make decisions about actuation, sensing, control, perception. Some things are hardware, some things are software, some are kind of in between, and some are even above, right? Regulations, liability. And the typical reaction, if you are a systems engineer, is to say, oh my God, there are too many components, too many objectives and choices to make, and nobody is able to understand the whole thing. And more importantly, which is bad for design, is we forget why we made choices, and we're afraid to make changes to these choices. So we need actually something different, right? We would need something faster where we can fail fast and execute, right? So I call this the anthropomorphization of the 21st century engineering malaise, these interconnected systems. And the diagnosis is quite simple, right? It's you lack a toolbox that is formal, quantitative, but also intellectually tractable. And I will try to iterate more on the intellectual tractability here. All right, so this is one challenge. You have many components. For these components, you need many domains. And these domains are heterogeneous, and you have components that interact in various ways. Now, not only they interact in a horizontal way, but actually these components also interact in a vertical way. In other words, your system is always just a component in somebody else's system, right? If I think about designing autonomy-enabled mobility, I could start from designing the sensors, LiDARs or these kind of things. Then you have to put together components and optimize the design of a vehicle. But then you have to put together vehicles and optimize the design of a service, fleet deployment. And now you have to consider that this fleet will interact with existing ecosystems. And so you have to coordinate the entire infrastructure. And now I could go one step up if I really want to abstract even further and maybe consider interactions of mobility and energy systems. Or here I could go even down a step and now think about the architecture of the perception algorithm or the design of the chip on which it runs. So you have many components interacting, but also many layers of abstraction. And now the third challenge is that in many of the systems I talk about, you cannot make all the decisions, right? Typically, these systems feature many stakeholders. For instance, for transportation, in Boston, you could think about an interplay between tech developers, academia, here represented by our president, Sally Kornblath, but also industry, policymakers, liability companies, and mobility providers. And now these people not only reason in different ways about the same problem, but also they have totally different languages to think about these things, and also different objectives, right? They don't care about the same things. So to summarize, you have large systems, many components, many natures, many objectives, but also strategic interactions between the players, which could be conflicting or collaborative. Now, if you have like immediate dream of dealing with all of this and finding a framework that solves all of these issues, you need essentially these 6 golden rules. That's what I believe. You need a framework that is formal and domain independent, that allows you to abstract away from the specificity of the problems in the specific domains and talk about really this in a generic way. But also you need computational tractability. You need to be able to find solutions to queries you have about your designs. You need to be able to talk about compositionality and hierarchy, these horizontal and vertical compositions, but also need to be able to, you need to be able to collaborate, right? To pool knowledge, for instance, in this room, in this virtual room of experts, and put it in the same framework. However, you need to do that in an intellectually tractable way, right? You don't want a system architect that's the only person that knows what's going on. You would like to distribute the ability to contribute to design. And finally, you want a continuous process. You want to be able to continuously adapt the design specifications. Now, in this talk, I will talk mostly about the first class of challenges. So the second one is an ongoing work, and I will touch I'll touch on some of the challenges there, but I will mostly focus on the first one. Now, the framework I'm going to present, it's a framework for engineering co-design, and co is really branding for collaborative, computational, compositional, and continuous, right? So this is exactly what we mean. It is designed to work across fields and scales, and it leverages domain theory, applied category theory, and optimization in the background. And the roadmap for the next few minutes is that I want to specify exactly what the problems are for the various components we care about. We will then talk about constraints of these kind of problems. And finally, I will show you how to solve these problems efficiently. So by the end of this talk, you will understand what the weird diagrams on the left that you can see on my papers actually mean. Those are design diagrams for certain technologies. And you will understand how to go from the left to the right to actually get some results to some specific queries, optimization queries. And now you might wonder why on a Friday in September, right at the end of the summer, you're listening to this MIT guy talking about category theory. You could have done something better. I agree that's a fair point. I will not talk about category theory specifically in the talk, but I will hide for people that know about the subject some key take-home messages or knowledge pieces in these pro boxes. And if by the end of this class of this lecture, or I convince you that you should learn about these things, we have a book coming up with Cambridge University Press that teaches this from scratch with no background knowledge needed. And I also have a class at MIT that teaches the subject with videos available online and slides available online. All right, so let's get started. To really understand this framework, you have to understand, you have to think about design essentially in terms of 3 spaces. You typically have the implementation space, so the options you can choose from. This could be the kinds of sensors you want to put on your drone. This could be the parameters of an algorithm, whatever you want to decide. They exist because they provide a functionality. They provide something to you that you want to achieve. And typically providing these costs comes at a cost, some requirements. And, people in systems engineering come from various domains, and depending on which domain you come from, you might know these things with different names, right? Functionalities are desired behaviors, specifications, objectives, guarantees, and instead resources could be budgets, requirements, dependencies, assumptions. So really, these things are quite common. And now the key intuition is that we want to be quantitative in modeling requirements and functionalities, right? Typically, requirements will be represented in red because it's something we want to minimize, and functionalities are something we want to maximize. We want really to get the best out of our system. And so those are in green, and think of them as things you want to maximize. And now I will insist in this talk that we are not used enough to think about trade-offs, right? These days, we are all focused on scalarization because we have tools, computational tools to deal with those things, but really there is a lot of value in looking at trade-offs. So for instance, you could look at two costs and a Pareto front between them, and essentially everything above is feasible, everything on the front is the best you can achieve, and everything below is kind of a dream, but you cannot achieve it. Or you can look at a similar front, but now between functionalities, and everything below is feasible, and everything above is unfeasible. Or you could look at a mix of the two, right? And then you have these kind of curves. So just to visualize trade-offs, this is a nice example we use in class for trade-offs of the human body, for instance, between speed and strength. You have Oleksiy Novikov, who is super strong, not super fast. And you have people like Usain Bolt that are very fast and not so strong. Both are feasible, right? They exist, but they are both faster and stronger than me, of course, and I lie in this very dominated sweet spot below here. Okay, so let's visualize what functionalities and resources mean. And since I'm Swiss, I come from Switzerland, I will bring a Swiss example, right? Which is the example related to watches. So let's pretend we have two implementations. One is a Casio F91W, and one is a Patek Philippe, right? We have resources, which could be costs. For instance, you have a price. The Casio costs much less than the Patek Philippe, and the Patek Philippe costs quite a lot, right? We could have two functionalities. Two functionalities, essentially. Being a watch, what does it mean to have a watch? Essentially, it could tell you the time, like the Patek Philippe, or it could tell you the time and also allow you to set multiple alarms, such as the Casio. And let's call this watchiness. Now, if this was the case, if these were the only resources and the only functionalities, you see that something would be wrong, right? Because essentially, the product that gives you more functionalities, in this case, the Casio, it's actually the cheapest one. So essentially, it wouldn't make sense for the Patek Philippe to exist in the first place. So is there anyone in the audience that want to suggest another functionality that would allow you to actually choose the Patek Philippe over the Casio? It's much easier to read the room when I'm in person, but I'm trying to do this exercise here as well.
Is it societal status? Although that's questionable.
I totally agree with you. That's exactly what I had. I had signaling, which is kind of a politically correct way to put it. But yeah, signaling is like, I'm somebody who can afford a Patek Philippe, and I choose to buy one. And I believe there's also some signaling in having a Casio, right? If you go, actually, between engineers, it's probably much more common to find people with a Casio because we like it, right? It's something cool. Anyways, this is just to say, as soon as you consider multiple dimensions, things are not obvious anymore, right? And I'm not the first one to say this, right? There's people in controls that have been around for many years talking about trade-offs. I always have this joke with John because, I put his, his picture in my talks where he went around for many years talking about trade-offs between being slow and fast and all the accuracy, flexibility, centralization, and so on of control actions. Now, in practice, what we care about is modeling these functionalities and resources, allowing to compare various quantities. And we want to do this in a way that allows us to also say that we are that some of them cannot be compared, right? We want to not always have somebody dominating something else. So as an example, so first of all, we use partially ordered sets to do this. And partially ordered sets essentially model total orders in various contexts, but also can model this idea that you don't prefer one thing over the other. So for instance, you could say I have a partial order of food preferences in Chicago, which is the closest to this seminar series. And you could say you prefer the deep dish pizza over other options, but between these other two options, you don't really have a preference, right? Now, on a more serious note, for instance, when you are designing motion planners based on some rules of the road, you could try to express some preferences over these rules of the road. For instance, say, I don't want to have collision. I want to minimize my collision energy. I want to minimize my area violation and clearance, but I really prefer collision over area violation and clearance, and area violation and clearance are equally important. Now, you can use this order to induce an order on trajectories, and those would be the trajectories, and those would be the induced orders. In another way, if you come from information theory, you might really care about ordering positive definite matrices, and this can be visualized by ellipsoids, and you could order them based on the inclusion of the ellipsoids, for instance. This is just to give you an example of things you can do with partial orders. Now, a bit more involved example involves trying to classify sensors and perception algorithm pairs in the context of trying to detect obstacles, right? You can characterize every pair of sensor and perception algorithm by looking at performance curves, right? False positive, false negative, and accuracy rates. Now, each one of these curves will be different, depends on the distance from the obstacle, and you can order these curves by dominance. And essentially, you can get some local partial orders for each one of those, and you can aggregate them at the end. This is just to say, partial orders allow you this extra flexibility of having uncomparable resources and functionalities, and we will model resources and functionalities as partial order sets going forward. Now, the second clear and key concept that I want to share is that on one end, we have functionalities, we have resources, we have the implementations that map to functionalities and resources, but the real question we want to ask is, given some functionalities I have available, does there exist an implementation that gives me at least what I want by requiring at most what I have, right? This is the only equation I will bring today in this talk, and essentially is a feasibility question. It maps each pair of functionality resource to the answer to the question, does there exist an implementation that gives me at least what I want in terms of functionalities by not requiring more than what I have? And this is a monotone map. Why? Because if I lower the functionalities, this should not require more resources. And on the other hand, if I have suddenly more resources available, this should not provide less functionalities. Now, this is what I call a design problem or a feasibility relation. But in technical terms, this is also known as a Boolean profunctor. And you can represent this as a box with green wires for partially ordered sets that represent functionalities, and with dashed wires for partially ordered sets that represent resources. So this is a formal language to represent these kind of objects here. Good, so now you might say, right, it's intuitive, but what do I do with this weird feasibility relation or design problem? Well, in engineering, you populate those, right? And you have various techniques to populate those. For instance, the first method is using catalogs. Sometimes you have existing technologies, and these technologies have properties, and you can relate these properties by the existence of the technology, right? For instance, you have a suite of drones. They have various properties, the flight time, the top speed, the range, and so on. And this could be either functionalities or resources. And by having a discrete list of options, you actually create a feasibility relation. So this is one way. Another way is actually going beyond the discrete case, in which you have things that are true independently of a particular technology, right? If you design a drone, the energy required by a mission is always greater or equal than the duration of the mission times the power consumption. This is always true, right? And the final method is what I call data-driven or on-demand, right? Sometimes you have some feasibility relations that are given by some discrete points. Those might be given by an experiment you run, a simulation you run, or even an optimization problem you solved for some purpose. And each one of these points, if put together, generates a feasibility relation. So this is really what can be used in many of the examples I will talk about later. So you have functionalities, resources, you have a feasibility relation, and you have ways to populate these feasibility relations that actually abstract away from a specific discipline. And now you might say, okay, but is this realistic? Like, do you have any examples? And here I tried to bring in some examples, but really the goal is that after this talk, you think about the things you care about, and you're able to design, to draw some boxes like this with some green and red wires, right? I am a Swiss researcher, so you could see me as a relationship between chocolate and Swiss chocolate, important correction, and the number of papers. I'm not saying quality, I'm saying the number. But more seriously, you could think about a mobility system as a relation between the demand and the complexity of the demand and investments and externalities. If you're into multi-agent autonomy, you could think about an area to cover, or essentially a task, and speed versus number of agents you need, the time you need to cover, or the total cost. If you are into assume guarantee contracts, this is a picture of a friend of mine, Alberto Vincentelli, who worked a lot on these topics, and we recently were able to show that these design problems I'm talking about actually generalize these assume guarantee contracts, where essentially the wires talking about assumptions and guarantees are specific partial orders that talk about sets of behaviors. This is just to say this language is quite universal, right? So you can discover or describe many different components with it. But the reason I really like it is not only that you can specify components, but it's because you can specify interconnections of components. I can take many of these design problems and put them together in various ways. I could put them together in series, essentially saying that the resources required by a component are provided by another one. I could put them in parallel. I could have a feedback loop between them. I could try to convince two experts, or trying to be robust to two experts. And no matter what I do, I end up with something which is, again, a design problem, something that has the same properties. So I can draw a box around this, and it's closed under the composition operator. And I can do this graphically as well, because this is a category, right? Behind the math behind this shows me that this is a category with some properties that allows me to compose this in this very rich setup. So this in practice becomes very useful because I'm now able to decompose large problems into sub-problems. Okay, so going back to the original quest, this is formal, and it's also compositional and hierarchical by nature. Now, compositional, it's obvious. I just showed you how to compose, but the hierarchy is also interesting, right? I could take this box now and plug it together in a more difficult interconnection of boxes, and that would allow me this vertical composition, this hierarchical composition. Good. So now, since I know there are a lot of control people in the room, I know that every time I mention the word feedback, people might get triggered, right? So I want to specify exactly what I mean by feedback. Here, feedback refers to the irreducible complexity or circular complexity of system design, right? Imagine that I want to design a drone. The drone requires actuators to be able to move, but the actuators must be powered by a motor, right? And but the actuators must be powered by a battery. And now this battery has to be carried by the drone. And the larger the battery, the more power I can provide. So the larger the battery, the more power I can provide, but also the heavier the drone. And so the more power I will require. And therefore you have this circular loop that reinforces itself. Now you could think of this also in general engineering setting, where you have some sort of externality of a system or a business case, and you have some engineering requirements that interact with the actual impact on whatever system you are considering. Now, I want to make the case for category theory, although you have not seen the exact math behind it. I want to essentially motivate it a bit, because sometimes when I present these things, people say, "Yeah, but is this old math that is becoming now popular really needed?" And the case I make in my class is the following, right? In various disciplines we are involved, that you guys are active in, you have developed very good mental models of systems, right? Some models are formal, some are informal. Some models are computational, some are not. And in general, we tend to use the most formal models to design, simulate, and analyze the systems. For instance, partially differential equations. Now, these models also help you communicate and share your ideas, for instance, at conferences or in a company and so on. Now, think of all these mathematics as a set of patterns that allow you to describe the world you care about. The unfortunate thing is that we are born in the 21st century, essentially, right? So engineers before us have solved a lot of problems, and the new problems we have to deal with complex systems, architectures, interactions, interconnected components. So think of applied category theory as an updated set of mathematical patterns that is particularly designed to describe large systems with these kind of interconnections. Now, what can applied category theory do for you and what it cannot do for you, right? You shouldn't expect a free lunch. Category theory is a mathematical theory. It allows to have theorems, methods, libraries of concepts you can reuse over and over. And also it allows you to visually represent all of this knowledge and to play around with diagrams in a formal way, right? You will see in my talk that you have a lot of these diagrams, and those are actually formal objects. Now, although these diagrams sometimes look different, actually they're always the same across different domains, dynamical system, optimization problems, and so on. And so you can use this fact to kind of abstract away from the specific discipline and reason about interconnections. Now, the category theory that is out there now still cannot solve problems by itself, right? What it can do is help you formulate the problem in a way that then finding the solution is easier, but it's not something that solves your problems automatically, right? It's not a small package you include in your Python script and will do the work for you. There is a catch, right? This is not something we tend to learn a lot about in engineering backgrounds. So you have to invest more work at the beginning, but the payoff comes later. And really, I wish I learned about this before even my PhD. I wish I learned about this earlier in my career. Now, I will make some cases in point today. Category theory has enabled a modeling toolbox for system design. It has enabled a tractable solution scheme for the problems. And finally, also, it has allowed many extensions, such as uncertainty modeling. Now, as I said, this is not something very common to engineering backgrounds, which is typically very heavy on continuous maths, such as analysis and so on, and very light on discrete mathematics. And the material you will find online is mostly dedicated to mathematicians, computer scientists, or software engineers. So it's rare to find actually case studies in engineering. So that's why a few years ago, we started creating a curriculum for engineering students or practitioners. And we have started writing this book, but also created this class. So if you end up being interested in this topic and you belong to the engineering community, I hope you will appreciate this. Good. So now I want to talk about solving these problems, right? I explained that we can generate these complex diagrams of interconnected problems, but what does it mean to solve them? There are essentially two queries, right? The first one is, given some functionality at the system level, I want to be able to find optimal solutions for each component that minimize resources. On the other end, I could be given some resources, and I could ask the question, how do I find the maximum functionality out of them? Now, these two problems are technically dual, and really, if I translate the first query, is how do I find a map from functionality to upper sets of feasible resources? Or if I really care about the actual optimal solutions, from functionality to anti-chains of minimal resources. Anti-chains are Pareto fronts, optimal minimal solutions. In this context, for designing an autonomous drone, it could be a trade-off between power consumption and the tracking error of the drone. Now, the one thing we're very good at in control, optimization, and robotics is thinking about optimization problems, right? So if I had to specify this in optimization problem language, this would be a class of optimization problems specified as a multigraph, where the nodes of the multigraph are these design problems, and the edges are the dependencies, right? These interconnections I was showing before. There are variables that are partially ordered sets for functionalities and resources, and the constraints are of two kinds. First of all, each node should be a feasibility relation, so you should have component feasibility. And second, each edge should be this series interconnection I was showing before, which essentially, you see, this is a partial order comparison. This is essentially saying that the resources required by a first box should not exceed the functionalities provided by another one. This is very intuitive, right? If a process requires compute, I can only use the compute that's provided by a computing unit. I cannot use more. And at the system level, I want to minimize resources, right? The resulting resources out of all the interconnections. So I want to pause for a second and notice that so far I only assumed this graph structure. I assumed the feasibility relation as the boxes, and I assumed the algebra of interconnections for all the various ways to compose problems. These problems are not convex. They are not differentiable. Actually, it's really weird to think about convexity and differentiability in this case. I will say this a bit more later. They are not continuous, and they are not actually even defined on continuous spaces. So if you are into optimization, usually this is very bad news, and you should essentially change job or switch to another problem. But the actually very nice success story we have for this class of problems is that you can find a solution, and you can find a solution quite efficiently. And now in the class, we actually dedicate 2 to 3 hours to actually go through the derivation of the algorithm and all the properties. But here, of course, I have to give you the more compact version, but I hope this will deliver the message. So a very fair assumption when you look at the smallest possible abstraction level of your design is that whenever you specify a component, you can easily essentially find this map from functionality to anti-chain of resources for the single component. What's quite hard, though, is finding the map for the entire graph, right? How do I find the resulting solution map for the entire interconnection? And what the methods we use in the background allow us to do is to have a compositional approach. Essentially, you can express the solution of the composition of problems as the composition of the solution of problems. Now, it looks like I'm playing just with words and I'm not really doing anything, but I defined some composition operators, and now I'm telling you that to solve this, I just have to find the corresponding composition operators for the single solutions. And the way to find this is a constructive one, and it's just actually using a functor between two categories, one of problems and one of solutions. Now, very concretely, this algorithm is a least fixed point algorithm of a monotone map in the space of anti-chains. It's a very, very exotic thing, which has two kinds of properties. First of all, this is a complete algorithm. So it gives you the set of all optimal solutions you care about, or a certificate of infeasibility, right? I am currently in Switzerland. If I say I want to be in 30 minutes in Urbana, infeasible, right? For now, one day maybe. And the second property is that the complexity is not combinatorial in the number of options, but it's just linear, right? So this is a very big, very cool news for us, right? Because we wish to create diagrams with many components, right? So if you have different design problems with A, B, and C options, this only scales linearly with these options. Now, there is a catch, right? Of course, which is that the complexity depends on the complexity of interactions, or the so-called feedback or co-design constraint. So this is computationally tractable with some asterisks, and I will tell you more about later. So long story short, we have a language to model design problems. We can exploit compositionality to solve them efficiently, and we can find all the solutions. And the good news is also, if you like these ideas, you don't have to learn any category theory to use it. There is a dedicated modeling language and a dedicated solver. So exactly as you might use CVX for some of your convex optimization stuff, you could start using this, where you can specify the problems and then solve them in particular ways. And by the way, we are organizing many workshops and tutorials on this, because really we want to get this out and have people try it and also be beta testers for some of these ideas. Now, I want to show you some applications of this where you actually use it and show you also how this works and what kind of trade-offs it can provide to you. So in general, when you look at these diagrams, you should abandon the vision that this is a signal flow diagram representation, right? You typically look at these diagrams and maybe expect the boxes to represent components, such as a sensor that produces data for an estimator, that produces an estimate for a controller, that produces a command. This is not the way you should look at it. What we really have is decision-making that requires a state estimate, that requires some sensing data, an algorithm or computation, that requires sensor, programmer, and computer, right? This is the way we look at things. And the typical thing you do is you perform a system decomposition or a functional decomposition of the system. You want to find the components you care about. And now, of course, the context informs the level of details. The way you use this framework is you first come up with the architecture you care about, and you forget about the way you're going to populate the various boxes. And how the boxes look like actually depends on what you care about, right? If you are a municipality studying autonomous vehicles, you might only care about speed versus costs. If you are Waymo, you might care about speed, distribution of scenarios, environments, specific cities you want to target, and not only cost, but also reliability, power, emission, discomfort, metrics, and so on. Now, once you come up with these diagrams, you can populate the models, and various models require various techniques. Now, a few things. First of all, many times you will be not sure about every component, right? Because you don't know everything. And with this framework, it's very easy to embed assumptions. Second is you don't actually need to have technologies that already exist. You can also play around with some temporal models, pretending that some technologies will be available, right? We are working these days with some companies that, for instance, want to design new sensors, and they might ask the question, okay, let's pretend this sensor adds these properties and at this cost. Would it change the state of the art today, in 10 years from now, in 20 years from now, and so on? And finally, although we did all of this in the same lab, this is kind of decentralized. You can add humans in the loop, and this creates very nice problems. So it is continuous, collaborative, but also intellectually tractable. Now, let's show a toy example. You could think of autonomous driving as following a trajectory and other things. Let's focus on following a trajectory. This could be lateral control versus longitudinal control, and longitudinal control could be speed tracking versus emergency braking. Now, with this decomposition, you can come up with a diagram where you essentially have different components for different processes, longitudinal control, lateral control, designing the computing, designing the perception algorithms, choosing which vehicle to automate, and so on. And depending on the buffs, you will have different methods to populate the feasibility relation. It could be, if it's control, it's simulation or optimization. If it's perception, you might have benchmarks. If it's computing, you might have a catalog of chips, and so on. Now, what I want to show you is, pretend you have populated these boxes. Now you will fix tasks. In this case, it's kind of specific trajectories and specific environments or curvatures of these trajectories. And, depending on the particular tasks, you will get different trade-offs. In this case, for instance, the error with respect to the control action and the total cost of your architecture. And for each point on this trade-off, you actually can extract the exact control strategies, the exact parameters of the algorithms, the sensors you're using, or the computing units. Of course, in general, you will have distributions of tasks, and it's very easy to look that with different tasks, you might get different trade-offs. And the monotonicity I was talking about before can be visualized here, in which you increase the complexity, for instance, by increasing the curvature of the maneuvers and the speed at which they have to be performed, and the kind of resources you require increase. Now, this is kind of a small toy example, right, where we are simplifying quite a lot the autonomous driving task. But with the student Dejan Milojevic, we have already extended this quite a bit in considering real scenarios with, classic motion planning tasks, perception algorithms, mounting positions of sensors such as lidars and cameras, and actual computation accounting with specific stuff used in the state-of-the-art autonomous vehicles. And these days we are working with autonomous driving companies to actually bring this to the state-of-the-art, where you might even get answers such as where to mount a sensor, how to use it, how to operate it over time, and so on. But so when I started this talk, I was a bit more grandiose, right? If you remember, the title of this talk is For Society Critical Systems. And so far, I've been talking about a specific vehicle, a single one, right? So my vision is really to use this kind of frameworks to put together at the same table people from different disciplines to design society critical technology. So for instance, mobility systems, right? The task here again is similar. It's demand driven. So the task is to serve certain demands, which might vary over time. And the things you are designing are the solutions, but also the network on which they act. And here you have various stakeholders dealing with these problems. So you could think, for instance, about designing an intermodal network where you have a fleet of autonomous vehicles, you have a fleet of micromobility options, and you have a fleet of public transit systems, the classic ones. And you also can walk around, right? And technically, every person can reach every destination starting from any origin by jumping on and off any of these modes as much as they want, exactly as you can do in real life. Now, you can model this as a co-design problem where you want to design the single modes, but also their orchestration, right? You can design autonomous vehicle fleet, the micromobility fleet, the public transit fleet, but also the orchestration. And if you start considering realistic cases, you take down networks and demand data from real cities, for instance, Washington, D.C., you can start actually looking at trade-offs. For instance, here we look at the case of Washington, D.C. in 2030, where you look at the trade-off between average travel time in the city, which is a potential metric that some municipalities are interested in, and the total investment they have to put in the system. So each point on this Pareto front is a possible solution. Each solution, you can extract it and look at the fleet size you have to use and the specific speed at which they have to drive. But also, if you perform this vertical composition, you can suddenly look at the detail of the autonomy stack for these specific vehicles you are using, right? And you can do the same for other modes. But really, what I want to say is that this becomes kind of a transparent framework through which people at this table can start reasoning and making decisions. And in transportation, this turns out to be quite important because, if you worked a bit on transportation, you know that you will never get any transportation researchers to agree on what simulator to use or what benchmark and so on, right? There are many schools of thought. And this framework, you can think of it as a democratic evaluation tool where now they could use, for instance, in the orchestration, various approaches, a linear program. For a flow-based problem, you could use a micro simulator, or you could use whatever you want. And now we're bringing this to the level in which you can get answers all the way from the software of a single box or a single, vehicle to fleet designs, right? So interactive fleet designs. And now we're bringing this to the next level by two important collaborations. One is with Sidara. We have a collaboration and a proposal ongoing where essentially this is a company that designs cities from scratch. And so we're really formulating the problem of designing a city from scratch, given a certain area and certain properties. And we also used to have a Department of Energy grant that unfortunately just got canceled, where we were bringing this to the city of Chicago to design shuttles, ride-sharing shuttles, autonomous shuttles for low accessibility populations. But the problem is very cool, and we're going to continue working on that, just unfortunately not with the Department of Energy money. Now, as I said before, we are working on many things in this context. You will read our papers, and we are applying this toolbox really broadly, and that's the goal. I want to be able to co-design everything, essentially. But I wanted to mention maybe briefly one very recent one, which is kind of exciting. I'm leading now a Center of Excellence in Compositional Optimization, where the focus is to apply these tools to multi-agent autonomy. This is with Air Force, and it's with extraordinary set of colleagues, including Ali Jadbabai, Alberto Vincentelli, Nick Matney, George Pappas, and Aaron Ames. And here the idea is really to not only design the robots themselves, so this is like the single robot design, but you also design the fleet composition, right? You want, given a task, to understand how to design your fleet, what is the capability of each robot, and there are various trade-offs, right? And also the architecture through which you control these robots. And there are various trade-offs. For instance, do you want to use robots that can do everything, like this very strange Caltech robot that can fly, walk, run, and so on? Or do you want to use a mix of robots? Maybe some are very basic, some are much more complicated. That's an open question, right? And there are many trade-offs: compute, performance, planning, and so on. And now, really, overnight, given that I was giving this talk, I wanted to bring some very recent stuff, we are working on in the lab, where, for instance, you want to, given the task of covering an area, co-design the planning, control design, with the design of the fleet or the composition of the fleet, right? And this is led by Max in my group, together with Yujun and Meshal. Say you might have various planners with various, techniques, and you might have various kinds of robots, ground robots, drones, and not only the robots, but batteries, perception, compute, actuation, and so on. And now, of course, this is again a co-design problem where you can design the planner, but you can also design the robots and their interactions. And in the very same way, you can get trade-offs for a specific coverage you want, where now, for instance, you can trade off the time needed to cover the area versus the investment to buy your fleet. Or you can also look at the energy constraints and so on. And every solution on this point is a particular fleet with particular properties and so on. So this is very exciting work. And although it might look different, we are applying these techniques in various other projects. We have one on Amazon Robotics, where you are co-designing the network on which these Amazon robots operate, together with the planning of and the execution of the motion. So you might want to change the network to simplify the planning and vice versa. We have now a project that's about to start with the city of Singapore for their new automated port, where you want to co-design the fleet again together with the network design. And although this thing might look exotic, we have another one on designing plantations and automated harvesting techniques. So this brings me to almost the end of the talk. I just want to mention quickly that probably you realize by now that some of these problems I'm talking about really require an extra layer of abstraction, which is the one in which these boxes belong to different people. So it's not really about optimization, but it's about finding an interaction of stakeholders with different objectives. So something we are really working on in the lab is this idea of extending this to co-design games, right? Where these boxes belong to different users. And now there are many things to do towards that. The first, even basic step is how to even think about games with this kind of structure. And that's, we have some ongoing work and some published work on partial order games. And also the other thing is many of these interactions are hierarchical, both in space and time. And so we are working a lot on game theory for these kind of things. And now I wanted just to quickly advertise recent work led by my student Minja on this idea of designing networks for transportation systems by leveraging competition and cooperation together, an interpolation between these two. And this work really started back when I was still in Switzerland, where you see this news, Switzerland pays 50 million euros to electrify the networks in Germany. And now you say, wow. So, the population really reacted in a way to say, wow, why are we spending money on somebody else's country, right? And this, although non-intuitive, it's actually a very good move, right? Because you can show, and you can read the paper. We also have this nice MIT News article about it, that if you can show that if you create an incentive mechanism for people to think about their own needs, but also to invest in other players, in this case, or in other regions, you can find better network designs, right? And better network designs under many performance metrics, not only the actual performance, but also returns on investment, equity, and so on. So to quickly summarize, my lab is working on a lot of these challenges, all the way from modeling and algorithmic foundations to the actual application to societal problems and user-friendly tools. Now, of course, this is all new stuff, right? So there are many questions. Many times, for instance, many of these boxes require you to get one particular point, one feasible point, you have to run a simulator, you have to solve an optimization problem, you have to call people at NASA that are experts to tell you some specific data points. And this thing is expensive. So you would like, ideally, to do an optimal sampling of the models. You don't want to pre-compute samples that you don't need, right? So the whole theory of the iterative version of this process still has to be developed. Another thing is sometimes people have reverse queries, right? If I show this to some companies or some industry partners, they might say, oh, very nice, this Pareto front looks cool, but I want a point here. Where should I put my money for you to give me a solution there, right? In which one of the various components should I invest my next money? Or how should I justify to my boss that I work on this problem? And those are kind of reverse queries that require a new sensitivity analysis and sensitivity analysis tools that we kind of don't have for these new exotic problems. And now something I wanted really to touch base on is recent work led by my student Eugene and Marius, where we were able to extend this to uncertainty accounting, right? In all of this, I never talked about uncertainty, but now we just developed a framework leveraging, again, category theory in the background that allows you to think about distribution of design problems. So now, if you have statistical data about your various components, you can embed them and you can start reasoning about problems of this kind. And now your Pareto fronts will be violin plots where you also have the probabilities for things. And this is very cool for many reasons: adaptive sampling, learning, stochastic optimization, you name it. So yeah, to summarize, new problems, a lot of things ongoing. I really want this to go out in the wild and apply it to many interesting cases. So So far, the cases have been limited by my experience, but I really want to hear more from you. And since this is new, you will notice on the web page, we are organizing a number of activities, all the way from writing books, workshop, interacting with authorities and industry. We really want this to go out in the wild. So if you go on with any take-home messages, we need new toolboxes for system design. And we think we have an idea, but we still need many people to work on it. And so far, multi-agent autonomy and society critical networks were the killer apps. I'm always happy to welcome visitors or hire. You know, I just started a year ago as a faculty. So if you have any questions, I'm happy to stick around and answer them. Thanks so much.
Thank you, Gioele. Thank you for the wonderful talk. Let's see if people have questions. Some just dropped out, I guess, on the top of the hour. Let's see if there are any questions.
Hello, hi, Gioele.
Hey.
Yeah, thanks for the nice talk. It's nice to hear about co-design problems and how to use them to solve couple design problems and so on. I have one question, like what happens, for example, if you are trying these methods for an automotive company and then they tell you, okay, regarding the longitudinal controller, you don't touch it because it's already certified and we don't want to do anything about it. You can just change the sensors or the actuators or whatever. So can you incorporate these kind of constraints into your approaches? Like if there is one block that you cannot touch?
Yes, that's a very good question. And actually, funnily enough, actually, let me go back to that slide. Funnily enough, that's exactly one case we had. So you mentioned automotive. We worked on a project together with Ferrari, the racing team part of Ferrari. So not luxurious cars, but the cars that actually are used in races. And there you have many boxes, as you say, that you don't want to touch, right? They come from decades of experience. Now, in the co-design framework, that's very easy, right? Because in the co-design framework, you just, let me go back to this generic picture I have here. In the co-design framework, the only thing you need to do with those kind of constraints is know which components depend on that particular component you're fixing, right? So if you have an architecture or you can come up with some sort of influence diagram or dependency diagram, then it will be a box where essentially there is only one option inside, which is the option they decided to fix, right? So that actually will simplify a lot the problem. Sometimes, in fact, it's nice that you mentioned this, because when we start working on problems with companies and so on, what they say is like, okay, we could consider all of these things, but let's for now forget about this component, this component, this component, let's fix them. And actually that simplifies the problem because it reduces the search space over which you have to optimize, right? So definitely we can do that.
Okay, yeah, thanks.
Actually, sorry, to add up on that, you can even go further and say, sometimes you fix a component, but it has some stochastic behavior, right? You don't really know exactly how it behaves. And with this uncertainty stuff I showed, you can model that as well.
Okay, yeah, thank you.
Thanks for the question.
More questions?
Hi, Gioele. I have a quick question. Sorry, pardon my background noise. Yeah. So very interesting talk. So the question I had is in terms of the output of the algorithm. So like I know it's not specifically just an optimization problem, which gives you a very like in the classical sense, you know, like but does it give you these trade-offs as an output or trade-offs like these Pareto fronts that okay. So the algorithm
it gives them as an output, yes. So the output is trade-offs and the list of, for each point on the trade-off, the list of design choices corresponding to that trade-off, right? And now for simplicity here, I plotted just two-dimensional ones because they are easy to represent, but really for many problems we have, 10-dimensional, 15-dimensional, right? And now there is a lot of work to be done on bringing those optimal solutions and showing them to the public in a way that is that they can parse them, right? You have to project, you have to show, but those are the solutions you get. Yes.
I see. So does the algorithm leverages the underlying solvers? So for example, as you mentioned that the box can be like a simulation or can be a linear program or something like that, which shows relationship between two between these ordered quantities, right?
Yeah.
So does the algorithm leverages those specific components, or how does that work, I guess?
The algorithm leverages those components. Now, the question you're asking is, I think I know where you're getting at, which is, oh, wow, so it means I can compose any kind of optimization or simulator and you will give me an answer. And the answer is yes, but with a catch, which is we're still developing the adaptive algorithm that actually allows you to sample with minimal computation, right? That's a very, very interesting research question, but it's also an hard one because essentially you have to develop it's kind of like differentiable simulation, but with none of the assumptions you have there and multiple objectives and these weird spaces. So that's actually an ongoing project we have right now.
I see. So one final question. So do you just need the requirement of to be able to sample from such a solver, or do you need a specific form of, like, what I mean by that is basically, let's say somebody gives you a black box of let's say a pre-trained feasible solution of corresponding to an input.
Yeah, you can also have a black box. The thing is, the more you know about the box, the more you can exploit it, right? If I know the box is a complex optimization problem where I'm just varying the constraints or varying the objective function, there is nice theory that tells you how various samples might interact with each other. If instead it's just a black, I don't know, sometimes you have these transportation simulators, which are, technically they're not black boxes, but you can consider they are black boxes by the number of things they are ongoing. That's harder, right? We are developing box agnostic sampling algorithms, but also box specific ones. Right? Say, the model is linear, the model is a convex optimization problem, and so on.
Okay, sounds good. Okay, so your website, as you said, would have hooks to these methods, right? Where I can go and find more details.
If you go to Zardini, my last name .mit.edu, you find everything. And I'm happy to answer. Send me emails if you have specific questions.
Sounds good. Thank you, Gioele. Thank you so much.
Thank you.
More questions?
Yeah, I have a question. So in this big box, you put these little boxes in there. So if you have a problem, is it always easy to set this architecture of the smaller boxes inside, or there are many times that there are multiple choices and it's not clear, and it's kind of an overhead there how you pick those this architecture?
This is an amazing question. Actually, together with Naira, we are thinking about how do I design the architecture itself, right? So this is a great open problem, and I'll give you an answer which is, it might be a bit confusing, but you can think of so there is structure that we are still not exploiting, which tells you that essentially each one of these diagrams is also a partially ordered set, right? You can also order these diagrams. And now each of these diagrams can become a wire or element of a wire. So now there could be a meta problem where you want to essentially iterate over the architectures. And this is a very interesting one, right? Because in some cases, for instance, nobody tells you that you should split the actions, right? Some people believe that for some cases, end-to-end architectures are the way to go, right? And you don't actually need to do perception control planning. So we are exploring that. But in all the cases you have seen here, they were fixed, right? You fixed the architecture and that was it. But I think there are very interesting cases to analyze where actually the architecture is a degree of freedom.
Yeah. Well, very, very interesting. Thanks.
Thanks so much. This is a cool question because it's actually something we're really writing proposals on at this time. So that's very cool.
Thank you,
Gioele, can I ask? Sorry, Naira. One small question that I had, and then maybe I can just go. So, is the existence of that functor mostly guaranteed? Like, what guarantees, like, or like what in what situations?
Yeah. The functor is guaranteed to exist, essentially by the structure we are using. These Boolean profunctors, these monotone maps that represent these boxes.
Okay.
And the nice thing is that, this monotonicity is very intuitive. in the very worst case, if you don't have monotonicity, you could have, although that makes the problem harder, you could have discrete partial orders. So essentially monotonicity comes for free. And, you know, you don't require this compositionality. Now, I can give you an extra step. We are currently also looking into adding more structure to actually design solvers or functors that are more efficient. And I can tell you, you know, the papers are not out yet, but I can tell you that if you make each box convex, a convex design problem, which has a specific definition, this is closed under composition as well. If you make it linear, it's closed under composition as well. So now there is an opportunity to, in case you have some boxes that have more structure, to use the textile structure to solve them more efficiently, right? And that's, for instance, what you could do in assumed guarantee contracts. Assumed guarantee contracts have a bit more structure, and those are a specific example of this framework.
Sounds good. Sounds good. Thank you so much, Gioele. Thank you.
Thank you.
Thank you. And if there are no more questions, we can close the link. I mean, you can later, if you have questions, email Gioele. If there are still last-minute questions, maybe you can take. 1, 2, 3. So we close. Thank you very much, Gioele.
Thanks so much, Naira.
We'll look forward to your slides for sharing, okay?
Yeah, I will share the PDF right now.
Thanks. Bye-bye.
Thanks so much and safe travels.